Okay, so I just did a proof of this theorem in the last clip, namely that if you've got an operator on V, then there exists a unique polynomial of minimal degree that vanishes on this operator, or in other words, so that P of t is the zero operator. And the proof that I just gave you, for that one, I used the Cayley-Hamilton theorem, which requires that F is complex, which in this scenario is not a hypothesis. So this should work for real and complex operators. So that's what the fault was with the previous one. Turns out that the proof for the general case is not that much longer, but oh well. Let's see, still better do it. So let's take n to be the dimension of our vector space. And then when we look at t squared, and we keep on taking powers of this operator, by the time we get up to t to the n squared power, this is going to be dependent because the dimension of LV is n squared, and we've got n squared plus 1 items in that list. And so this is actually going all the way back to 3.61. Okay, and then from somewhere else way back in chapter 3, or maybe even chapter 2, actually, in chapter 2, there was a lemma that said, you know what, if you've got a dependent list, then there's a first place where it becomes dependent. So we can choose m to be that first place. So choose m to be the smallest integer for which the list t squared up to tm is dependent. Okay, so then Tm is going to be in the span of the foregoing powers of t, like so, which means, or which implies anyway, that there exist coefficients ak in our field with a0 times the identity plus a1 times t plus up to a m minus 1 t to the m minus 1 being equal to minus tm. And so then if I put tm over here, I get 0. So I can solve this equation, right? And so here there's like a coefficient of 1, and that's precisely so that the thing that I get is going to be monic. Okay. And so if I then define a polynomial with these coefficients, then P is monic and P of t is 0 by construction. Okay, so we've got existence. For uniqueness, we do the same as before. So namely, if there's some other polynomial with same degree that vanishes on t, then q minus p by linearity is also going to, or by the definition of q minus p, is also going to be equal to 0. And by the fact that they're both monic, the degree of q minus p is strictly less than the degree of p, which violates minimality. Okay. So there we go. A legit proof that works now even in the complex case. So it also follows from this result that the degree of the minimal polynomial is no bigger than the square of the dimension of the vector space that you're looking at. And if we have that we've got a complex vector space, then the degree of the minimal polynomial is going to be bounded by the degree of the characteristic polynomial, as we saw in the previous clip, which is equal to the dimension of v. So that's a big improvement from dim v squared all the way down to dim v. And that follows by Cayley-Hamilton. And then in the next section, we'll see that the degree of the minimal polynomial is bounded by the dimension of the vector space V for the real case as well.